So regarding EDFA, what it has is it has a pump laser. So I said it's an optical pumping system. So there is a laser which is pumping a piece of fiber, and this fiber is the fiber I was mentioning to you earlier. It is doped with, it's a silica fiber doped with erbium. The length of the fiber could be anywhere between 5 meter, 10 meter, 50 meter or so on. You couple the light from the pump into the fiber. You could couple from either side using this optical coupler. Here is where you give your input signal, and here is where you get your amplified output. Okay, and this technology was made possible in mid 80s. 1985 was when rare earth doping process was developed without adding the background loss. So, a lot of this work was to do with the glass chemistry as to how to do this doping. People knew that erbium had emission in 1550 nanometer, but the problem was how do you come up with the technology to dope a silica fiber with erbium without causing additional loss in the system, and at the same time providing a large gain. And this was done in simultaneously by two groups. One was David Payne's group. It was a completely academic group in the University of Southampton, and the other one was done by Deservier and Randy Giles in AT&T Bell Labs in France. Okay, so both of them get the credit of this patent, and it was in 1987 that the first optically pumped amplifier, erbium dope fiber amplifier, was demonstrated. Of course, it was demonstrated with argon pumped dye laser, and it was not at all an efficient system. They had consumed 80 kilowatt of electrical power to actually do this, but later on the process, the glass chemistry improved, the process improved. Right now the power required to pump up a erbium dope fiber amplifier, electrical power required is much smaller. It's the current drawn is about 500 milliamps or 1 amp, and so the power would be into a 50 ohm or into actually a 2 or 3 ohm diode. So the optical power that is consumed by an EDFA is very small, and that's how it became very popular. We will go on now to the details of how this EDFA is working. So to recap on light matter interactions, this is something that we have done already at the beginning of the course. We say that light and matter can interact in 3 different ways. There could be spontaneous emission, there could be stimulated absorption, and there could be stimulated emission. With a spontaneous emission, you don't need anything to initiate the process. You have the electrons or the ions in the upper state de-excited to the ground state randomly, and so you have spontaneously emitted photons. So this cartoon just shows 2 energy level diagrams, E1 and E2. E1 is your ground state and E2 is your upper state. N1 and N2 are the population densities, which is population per unit volume in these states, and you know that the rate of emission is this is something that we had similar in a laser theory we did. It is proportional to the rate at which you the population is de-exciting is proportional to the N2 itself, and you can write it as equal to minus N2 by tau, where tau represents the lifetime of the excited state. Now if it is stimulated absorption, okay, so the difference between a semiconductor system that we had discussed earlier and the erbium system is, here we are talking about the excitation of erbium ions, there we were talking about the excitation of electrons in the valence and conduction band. So here I will be talking about ions which are erbium ions which are going to be excited. So in stimulated absorption, what happens? All the ions are in the ground state. You pump your system with light and the ions get excited into the higher energy state. So you still have E1 and E2, with E1 populated to start with, and you have photons in going into the system, and you will have absorption happening, and the rate of this absorption is given by the photon flux density, because how fast you can absorb is decided by how many photons per unit time are you able to pump into the system. And it is also dependent on something called as absorption cross section. This absorption cross section is a statistical number which tells you the probability of absorption. So this absorption cross section is measured in the unit of meter square. It tells you what is the probability of absorption. For instance, dN1 by d2, the rate at which this process happens, is proportional to this probability, and it's proportional to I by h nu, the number of photons that are falling on the system, and it's also proportional to the number of ions in the ground state, right. So this is your rate equation for absorption process. Of course, phi nu is the number of photons of frequency nu per unit area per unit time. So to compensate for this per unit area, this sigma A is having a unit of meter square, right. And I nu of course corresponds to the intensity, and intensity divided by h nu gave you the number of photons. So the phi nu is I nu divided by h nu. And of course you are talking about unit time because you are talking about the rate of absorption, right. But the third process is what is more interesting, which is stimulated emission, which was resulting in lasing. So in stimulated emission, we have, if you remember, we said that the prerequisite is that you need to have a population in the excited state, so that whenever there is an incident photon, the probability of absorption is low, the probability of emission is large. So whenever there is an incident photon, it initiates a transition, coherent transition from the higher state to the lower state, resulting in coherent emission of radiation. And this rate is given by, again, emission cross section. The rate at which this upper state is depopulated is given by emission cross section, which is again a probabilistic quantity, and its unit is meter square. This is the number of photons per unit time, and N2 is the number of ions in the excited state per unit volume. So N2 is per volume, this is meter square, this is I by h nu is a number of photon again, and of course this is per unit volume. Now as we all know, this is the principle of the lasing systems. The only difference in between an amplifier and a laser is that in a laser, this photon comes in from one of the spontaneously emitted photon, that's what feeds back into the system, whereas in a EDFA, it is just a laser without the feedback element. So there is no feedback, this is not there, this is my input signal. This input signal needs to initiate this transition from the upper state to the lower state, so that you have an output signal which now is magnified or amplified because of this large number of photons that are present already in the upper state, and that is how you get an amplification. So in that sense, the output signal is coherent with respect to the input signal. It will have all the phase polarization properties as that of the input signal. So that is why your system is polarization insensitive. If your input polarization is X, your output polarization is X. If your input is Y, the output is Y. The amount of gain that you can get now, how many photons come out because of one photon at the input, is now decided by how many ions were there in the excited state. So you still need a population inversion in an EDFA, but you are not using it for lasing, but you are using it for amplification, right? And of course the gain element is silica fiber with erbium ions. So we are using this principle of stimulated emission to make a erbium doped fiber amplifier work. Now what are the critical parameters? The critical parameters is the gain spectrum, how broad your gain is going to be. So for that, to understand that, we need to look at the energy level diagram of erbium. Now erbium is will present itself as triply ionized ion in silica, right? So that is why it is referred to as ER3+ ion in silica. in case of semiconductor, we just had two states. We just broadly said there's a valence band and there's a conduction band. Instead, we have three energy levels. We have E1, we have the upper state E2, and we have upper state E3, and we have the metastable state E2. Now, if you were to, so this is what is called as a 3-level lasing system. Unlike the semiconductor where we had a 2-level system, you had just 2 levels, valence band and conduction band. Of course, they were not levels, they were bands. So the key is erbium, the excited state for erbium is corresponding to this E2 level, and there are a couple of ways to bring the ions to the E2 level. Remember, you need to have ions in this state populated very well so as to initiate the lasing action. To bring these ions to this level, there are a couple of methods. One is you can pump it with a laser whose wavelength corresponds to, or whose frequency corresponds to E3 minus E1, and that wavelength corresponds to around 980 nanometer. Or you could directly pump it with a 1480 nanometer laser, which corresponds to the difference between this and the uppermost state here. Now, these are ions in silica, so they are supposed to be discrete levels, but as written here, the energy levels are actually bands because these ions are physically present in the electric field corresponding to silica, and in the presence of electric field, this is the electric field corresponding to the crystal, the field that holds the material as a crystalline material. So, because of that internal electric field, these are not single levels, these are just bands, right. So, these are because of what traditionally in atomic spectroscopy what we learn as Stark splitting, where when you apply a large electric field, the individual electric field will split into multiple of levels, and transitions corresponding to the selection rules are allowed. So, rather than going into the details of the Stark splitting, we can just assume that E1, E2, E3 are not independent levels or discrete levels, they are a continuum of levels, and with the result that the transitions are not corresponding to a specific frequency, the transitions correspond to a band of frequencies. Okay. Now, what are those band of frequencies? That is given by the emission and absorption spectrum of erbium. So, this is the emission and absorption spectrum of a commercially available erbium doped fiber in silica matrix. So, you see that the dashed line is the emission cross section and the bold line is the absorption cross section. Of course, there is a strong absorption at 980 nanometer also, which is not shown in this plot. The plot ranges only from 1450 to 1650 nanometer. It tells you that what it does not tell you is there is an absorption at 980 nanometer, which is not in the scale of this plot, but it also tells you that you could have an absorption of energy in this range, which is given by, and the strength of probability of that absorption is given by the bold line, and with about at 1480 you see a larger absorption here, and the same band you can have emission also, and the probability of emission, there is no probability of emission at 1480, it's very less when compared to absorption, but at the same time the probability of emission goes higher in the longer wavelength side. Right. Longer wavelength side would mean smaller energy, which also means that whenever there is an emission happens, it is between the lower levels, whereas the absorption it is to the higher levels. So, it means that you can the incoming photon is of energy 1480, it gets absorbed, it goes to the higher state. There are these intra-band transitions which will bring these ions to lower states, and when they emit you get emission probability larger at longer wavelengths. So, this figure is only telling you the probability of emission and probability of absorption. The question is how much of emission do we get and how much of absorption do you get. As I said earlier, you could pump both at 980 and 1480 nanometer. Commercially, EDFAs are available with both 980 pumping and 1480 pumping. There are small benefits or disadvantages for each of these systems. We will not go into those details. But as far as the communication system is concerned, both of them are equally acceptable. What is to be noted here is that it's a broadband emission and broadband absorption. But this picture may give you an impression that it is not flat at all. You want a flat gain at in the C band. C band is somewhere in 1530 here and 1560 here. In this region, the emission is showing this behavior. So the answer to that question is that this is only telling you the probability of emission and probability of absorption. The actual gain spectrum is decided by this probability, and also it is decided by what population you have in N1 and N2 states, because that is why earlier we wrote down the rate equation and we found that the rate of emission is decided by the population in N2 and the rate of absorption is decided by the population N1. Population densities N1 and N2 decide how exactly this emission and absorption are going to be distributed. So the simplest way to understand how the spectrum is going to look like, the gain spectrum is going to look like, is say that the small signal gain is, so this is the emission probability, which is a function of lambda, because we just saw that the emission and absorption cross sections are highly dependent on lambda. So this is the emission cross section times N2, because N2 is the population in the upper level E2 and N1 is the population in the lower level E1. So this gives you the probability of emission or the number of ions that are getting emitted, and sigma A times N1 tells you the effective absorptions in the system, and emission minus absorption is what would you count as gain in the system. So the gain is effectively the subtraction of, or rather you count the emissions and you count the absorption, the difference should be the gain, right. So the small signal gain is, when you say small signal gain, it simply means that the gain per unit length, it's per unit length quantity, because this is of magnitude m square. This would be of 1 by meter cube, because N2 is a population per unit volume. So multiplication would be per meter, right. So the small signal gain is the gain per unit length for a erbium doped fiber amplifier system, provided you know the emission and the population in each of these gains. Now there is an additional factor gamma here. This gamma tells you that within the fiber this inversion is created by pump, optical pump, which could be single moded, which should be single moded, and that will have a distribution like this. And if you remember your theory of single mode fibers, if you go longer in wavelength, your signal, so pump is at 980 nanometer or 1480 nanometer, signal is at 1550 nanometer. As you go, as the lambda increases, the modal profile actually spreads more and more into the core, right. So the inversion happens, population inversion happens only in that region where the pump is flooding where the fibers actually experiences the pump intensity, which is like a Gaussian profile, and the signal gets amplified only in that area where the pump has created population inversion. So essentially we are talking about the overlap between two Gaussian profiles. Only in that overlap region will you see the gain. You won't, so signal is, so this is the signal which is having a larger spread, this is the pump which is having a smaller spread. So the signal does not experience gain all through, it experiences gain only due to the ions in the fiber which are exposed to the pump. So that is why you multiply it with the overlap integral. and that number is given different for 1480 nanometer pumping and 980 nanometer pumping, simply because the modal profiles will change when the wavelength changes. This is something that we did in our theory of single mode fibers. So that's the reason this gamma is important, and because of that the G value that you will get for 1480 pumping and 980 pumping also would be different. Okay. Now it turns out that now this gain is going to be dependent on what is in your N2 and what is N1. Now what is N2? N2 is a population density in the upper state, N1 is a population density in the lower state. So this it's not just independently dependent, it's not just dependent on N1 and N2, it is actually dependent on, you know, a factor times N2 minus N1. So it's good to define something called the inversion. Inversion tells you what fraction of my total ions are present in the excited state. So you define a quantity called as inversion, which is N2 minus N1 divided by rho, where rho is N1 plus N2. The total ion dopant concentration. Let's say you are doping the system with a certain concentration. These erbium ions have to be found either in the ground state or in the metastable state. So the ground state population density is N1, metastable state population density is N2. So the total ion density is N1 plus N2. And you define a quantity called as inversion D, which is N2 minus N1 by rho, or which is N2 minus N1 by N1 plus N2. So that if D is large, it means that there is a large inversion. And when there is a large inversion, it means that the probability of emission is going to be large because you have more inverted ions. So defining this D, you can rewrite this above equation in terms of D this way. So it's just an algebraic manipulation. Instead of N2, you wrote it as 1 plus D by 2 times rho. Instead of N1, you wrote it as 1 minus D by 2. You can easily prove that 1 plus D by 2 is nothing but rho times 1 plus D by 2 is nothing but N2, and 1 minus D by 2 times rho is nothing but N1. The reason why we are doing this is because now we can define this in terms of one unknown parameter D, which is telling you the level of inversion. And you can keep inverting more, in the sense that you can keep having a larger inversion just by increasing your rate of pumping. As you increase your pump power, this D value keeps on increasing. And so my gain is now, I can write in terms of D. So I know that sigma A is a function of lambda S. I know sigma A, I know this sigma A as a function of lambda S. That's what we saw in the previous slide. I could use that nature of variation, and I can calculate the gain as a function of inversion. And if I plot that, this is how it is looking like. This is gain per meter for an erbium dope fiber amplifier for different levels of inversion. So here I go increasing D. It means that, for instance, if you see 1530, this is your C band, right? So C band is 1530 to about 1560 nanometer. This is the range of C band. This is the range of C band. In this band, so in this C band, you see that for instance, if you are choosing an inversion like this, you have almost a flat gain, right? So you can choose your appropriate inversion, and how do you choose your inversion? You have to have a large N2 minus N1 or small N2 minus N1. And how do you decide that? You can potentially change your pump power, and as your pump power increases, the population in N2 and N1 will change, right? So by controlling the pump power, you can, so increase in D is usually with the increase in pump power, and with that you can achieve almost a flat gain in the C band. So this is a typical amplifier response. If you take it from 1520, for instance, your peak is the gain, there is a peak at 1530. So if I take from 1520, there is a peak here. This is the typical amplifier response. For the normal use condition, you would want a flattened response. So how do you get a flattened response? Commercial at first, what they do is they find the error between this flattened response and your actual amplified response. So this is the error. So if you subtract this error from your original signal, you will get this flattened response. So the question is, what is the consequence of not having a flattened response? If I do not have a flattened response, I don't have a problem for single channel system if my wavelength is fixed. But suppose I have a single channel system, but I am changing my wavelength of operation. If I am operating at 1530, I am getting amplifier gain of 28 dB. If I am operating at let us say 1540, the amplifier gain has dropped to 4 dB, which means in my link budget I will make an error of 4 dB when I go from 1530 to 1540. Otherwise, what I should do, I should be building some intelligent system to make the link budget at this number, and whenever there is a 1530 coming in, I have to put an attenuator which will bring the power down and so on, right? So you will have your network will have to be much more intelligent if my amplifier response is not flat. So all commercial amplifiers would necessarily require a flattened response. So how do you flatten the response? The flattening of the response is quite straightforward. You build your amplifier, you find out what is the error, and you put a optical filter bank, a dielectric filter designed such that the transmission response of that filter exactly looks like this. So that is equivalent to, so you usually have an EDFA followed by a optical filter, and that optical filter will correct for this difference. Gain flattening should be such that the difference in gain should be less than 1 dB. Those are the kind of requirements you want to put in. Now these optical filters could be a bank of FBGs, fiber Bragg gratings, or it could be dielectric filters, or it could be a liquid crystal based filters. There are different possibilities that one can think of. So if you just take an amplifier, doesn't matter what your inversion is, you will always have a non-linear non-uniform response, and you have to correct for it if you were to use it for a commercial communication application. So that's about the gain spectrum.